Um, I thought, what am I going to do in 45 minutes? Not a huge amount of time to talk about machine learning. And I wrote down a list of things I thought I ought to cover, which I'm not going to read to you, and that's the list of things. And by the end of this talk, it is my hope that you will understand those and you will understand them in the context of machine learning. But then you're faced with a problem. Am I just going to sit and define everything at the beginning? So here's a definition of induction. Here's a definition of deduction. That's going to kill people. That's so boring. So I thought the other way I'd do it is just start talking, giving you examples of machine learning and use those to illustrate all the terms on the last slide. There's the last slide. All those terms will get defined by the end. That sounded to me like far more fun than reading lists of definitions. So we'll start with a really simple example of machine learning. So imagine that we are an advertising agency. We're given a budget by our clients and we spend that money on partying. Sorry, we spend that money on advertising their products and services. That's our business model. We've been doing this for a while. We've worked for quite a number of clients. We have also been sensible enough with our clients to say to them, how much profit are you making here in this period before we run the advertising campaign? And then during the advertising campaign and afterwards, how much profit do you make then? And we collect that data and we know how much we increase their profits. And actually, despite my joke about partying, we are actually a very ethical agency. So a new client comes to us and says, if we spend, let's say, 25K with you, how much additional profit would you predict that we will make? So what we would do at that point is examine our data carefully, clean it, prepare it, and then we elect to use linear regression to answer the question. And here is exactly the same slide, but with those words highlighted. First thing you do in machine learning is just look at the data, you eyeball it. This is a really important part of the work. You can't just start throwing machine learning algorithms at data randomly. The first thing you'll do is look at the data, kind of smell it, taste it, listen to it, get a feel for what it looks like. Only then can you decide what algorithms or what machine learning techniques you might use on it. I've also put in there the words clean it and prepare it. 4 little words, tiny words, huge amount of work very often. Those of you who have worked with data a lot will groan with the pain of trying to clean the data that you're provided with. If you don't, if you've never had to clean data, I want to work for your company because I've never come across a company that provides clean data. They always provide data that's flawed. It's the nature of data. So I'm completely and utterly not trivializing those 3 steps: examining the data, cleaning it, and preparing it. I'm just not going to talk too much about them on this talk because we want to talk more about machine learning. Although those are part of machine learning, you have to do those. So we like to use linear regression as a machine learning algorithm. Well, why? Why did we choose that? I'm going to list for you some of the main types of machine learning we can do. One of them is linear regression. Why would I choose linear regression? Well, one reason is I might just look at the data and I might find that along the bottom here, it's not labeled actually here, but this is the amount that we spend on the advertising campaign, and this is the amount of the increased profit. Actually, this is just a generalized graph, but linear regression looks at these points and tries to fit this line in the best possible place. So it tries to fit this line in the best possible place. To put that slightly more accurately, it's predicting the values of y from the values of x with the least error. So given that this client has asked us to predict the profit from the spend, this is not an unreasonable place to start. Is it the only form of regression we can use? No, there are lots of ways of joining those points. Here I have played join the dots. This is usually not a good algorithm, incidentally, for prediction, but it's one possible way of linking X and Y. here you can see I'm trying to fit a non-linear regression to a set of data that is pretty linear. So I might well have looked at this data and decided to use linear regression. That's never going to be an absolute decision. It'll be the first thing I'll try. I might try something else. And that is something else to bear in mind about machine learning. It is often a process of try something, if it works well, carry on. Otherwise, backtrack and try something else. That's the reality of machine learning. Okay, I have a table of data, and you'll notice how beautifully clean this data is and therefore unrealistic. But there's, for example, a spend we made on one advertising campaign. There's the increased profit that that company made. Not a good deal, that one. Here's another one. Let's choose one that puts my company, our company, in much better light. We spent 20K and they made an increased profit of 36K. So each of these I don't know if you can hear that. That really is thunder overhead. So if I disappear,
we can hear it.
You can hear it, can you?
Yes.
Yeah. So if I disappear, either I've been struck by lightning or the power supply has, and I'd much rather it was the power supply. So we have our X coordinates and our Y coordinates. That's the spend, that's the profit. Okay, so we've got some data. And with machine learning, clearly one of the most important things you have is data. We've chosen to plot profit against spend, and we're going to use linear regression. To put that in machine learning terms, we're choosing linear regression as the algorithm that will be applied to the data. I just want to digress really briefly on this word algorithm. An algorithm, in broad terms, is just a way of solving a problem. It actually doesn't have anything to do with computing. Algorithms were designed long before there was computing, but computers are very often used to implement algorithms. And we tend to talk about machine learning algorithms. We'll talk about a clustering algorithm, a neural net algorithm, linear regression algorithms. So this term is just talking about the generalized technique that we're using. So we've elected to use linear regression. So we've got some data, we've chosen the algorithm. And clearly what I'm doing is spelling out along here the kind of process that we use in machine learning. First thing, get the data, clean it. Next thing, you've got to choose an algorithm. Third thing is we then actually use the algorithm. We apply the algorithm to the data. And in this case, what it generates is a line of best fit, and it generates the equation of that line. And a lot of you may remember from school, the old idea, the equation of a straight line was y equals mx plus c. And you can see
Mark,
that.
if I could interrupt you for a second, I'm just
Sure.
going to, there's a lot of background noise and people are mentioning it. So I'm just going to mute all and then unmute you. If you give me a second. That
Sure.
would be, okay, let me do that. My apologies for this. I'm going to just mute all. And you have to unmute yourself, Mark, I'm afraid. If you unmute yourself. Ah, good. Mark? You need to, Mark, could you unmute yourself?
I was trying.
Sorry, that's so much better.
Reach.
We're having lots of background noise and I was getting some chat about it. It's perfect now.
Well, the good news, I'm unmuted. Just kidding.
I'll do that again if we get the same problem. I'll give you a warning. Don't scare me, Mark.
A bit much. I dropped out there. Am I back?
Yes, you did. You dropped out for about 20 seconds.
Oh, that's okay. Sorry about that. It's telling me the meeting's being recorded.
Yes, it is, but not for distribution.
Oh yeah. Okay, so let's carry on. Okay. Sorry, I've just got to rearrange these screens. That's okay. Right. So y equals mx plus c. So we've got the data, we've chosen the algorithm, we've applied the algorithm, that is, we put the data through the algorithm, and it's generated that equation and that line. So we've created the model, and sounds like somebody's dying. Then we can remove, what we can then do is we can essentially remove the data, and that leaves behind just the model. And that's quite an important point, that actually what we want from all of this is just the model. And in fact, what we want is just that equation.
This spring with this pandemic.
Mark, it's best if you mute all people rather than me doing it, because you can do that. You can just mute all. Someone's coming on and chatting. But if I mute everybody, I'll mute you.
I have enough screens open not to be able to.
Okay, no worries. If I mute everybody and then you unmute yourself.
Okay.
Let me unmute. I'm going to mute all right now. So you just.
Haha, I'd moved the unmute button, you see. I'm getting wise to this.
That's good. That's good.
Okay, so.
Solve the problem.
Quick recap. Oh, we wanted a quick recap roundabout here anyway. We're doing machine learning. We've got some data. We've got some data. We choose a machine learning algorithm. We use that to create a model. And at that point, you can then actually remove the data. Now, I don't mean you delete the data. Nobody's going to delete data, but you remove it from your consideration, because all you want is actually just this model, because this model is a distillation of the information in the data. And that's a good way of thinking about it. And in fact, we might have started with 20 million data points, but the data model then encapsulates the actual pattern or information in those 20 million data points can be summed up as simply that. And that's a really common thing in this modeling we do of data. We can take a vast amount of data and distill it down to a tiny amount of really useful information. And that's a good way of thinking about machine learning. It's not the only way of thinking about it, but it's a good way. Okay, so going back to our prospective client, they wanted to spend 25K. What do we predict the profit will be? And just by plugging the numbers into that equation, we get the answer. We would expect your profit to be 58K. If we want a visualization of that, fine, we can plot that on the graph. But actually all you need is that equation. So there, here in microcosm, you see the actual process of machine learning. And when I put it up like that, I think it almost looks like I'm bluffing that, because machine learning, we all know, is very complicated. It's very complicated stuff. Well, you can describe it as complicated to your clients to up your daily rate if you like. But machine learning is actually a very simple process. And it is exactly as I described there. Now, you can make it more complicated. We could use much more complex algorithms than linear regression. And clearly I chose linear regression because it's a nice, easy one to visualize. Why would I choose a hard one to illustrate it? But actually, that's just detail. The actual process of machine learning is what you see. Now, to give you some idea of how that process can become more complicated, and we can just add detail to it. A good example of why we would add detail and make it more complex is we create this model here. But a good question is, how good is that model? Is it a really good model or a bad one? And unless you test it, you're never going to know whether it's any good. So one of the things we really commonly do with machine learning is build the model, create it, and then test it to see how good it is. And the way you test it to see how good it is, imagine that you have a large block of data, so a big block of data. You could use all of that data to create the model. This is this kind of data. So it's data that looks like that. It's that kind of data. I could use all of the available data to create that model. Another thing I can do is take 70% of that data and create the model. And I keep back 30% of the data where I actually know what the answer was. I know what the marketing spend was, but I actually know what the profit was as well. So that 30% there is not used to train the model. We're using that 70% to train it. This 30%, once we've built the model, suppose one of these numbers is we spent £27,000 and we know that the increased profit was 47. We can feed in that 27 and say to the model, what would you predict that would be? And if the answer is 46.9, we're very smug because our model is good. If the prediction is 109, our model is clearly rubbish. And I'm not suggesting we test it with one single example, but you get the idea. So one of the things we do with machine learning is use some of the data for training, typically 70%, doesn't have to be that, but that's what we would normally use. And then we test it with another 30, the remaining 30%. So that's something to know about machine learning. That's really common. Another kind of detail is that actually you can stop at this point. You can use the data, you can choose an algorithm, you can create a model, and you can stop at that point and not use it to try and predict future work. So not use it when a client says to you, I want to spend 25K, not use it to tell them, well, that's going to bring you 50. If we stop at this point, this is called data mining. And data mining has been around for a long time, and it's looking for patterns in data, but not then applying that pattern to future events. Why would you do that? Why would you want the pattern if you're not going to use it? Well, you would use it, you just use it differently. Suppose, for example, that I'm running this agency and we do it and we discover that it is actually a linear relationship like this. Or suppose we get the pattern out and the pattern is like that. Now, if I'm an honest person and a customer says to me, we want to spend 50K with you. Should we spend 100K with you? Well, that makes us twice the profit. Well, if I see that relationship, then I would say, yeah, spend more and we'll make you more money. If I see this kind of relationship, if that's the pattern I see through data mining, and they say, well, should we spend more money than this? I'd say, no, you're wasting your money. Spend up to this point, but don't spend any more. So there are times when we use these algorithms to look for the pattern, and actually what we want is the pattern. We don't actually want to apply it to future events. So that's data mining, and we can generally use the same algorithms for data mining as we can for machine learning. And that's why there's so much crossover between these two. If you look at a list of data mining algorithms, you'll find they're typically pretty much the same as machine learning algorithms. The crucial bit that makes it machine learning is if you store the model and then apply the model to future data. So really simple. Okay, so a quick summary of where we've got. We take training data, put it through an algorithm, and that produces a data model, which is a distillation of the information in that. In our case, I had my XY coordinates, I used linear regression, and that produced a data model which was a line. Then we used the data model to predict the future. We often use training data and test data, training data to create the model and test data to verify how good it is. And note we have not very formal, but we have formal processes for checking the accuracy of model. Things like ROC curves and so on are very interesting ways of testing the accuracy of the model. And that's an area you can spend a vast amount of time learning about. So I am just giving you the kind of overview of machine learning here. So what have we covered so far? From my list, we have covered difference between training and test data. We've talked about machine learning as a process, and we've talked about linear regression. Where are we going now? Well, we're going to have a look at a couple more machine learning algorithms, just in brief. But I'm also rather sneakily going to use those to introduce supervised versus non-supervised learning as a term, because it's useful. So here's a list of machine learning techniques or algorithms. All of these will also appear in lists of data mining algorithms for reasons discussed. This is not an exhaustive list, but these are the generally considered the kind of main machine learning techniques. Notice I've stuck neural nets in at the bottom, describing them as modern. So what we're going to have a look at are these two guys, classification and clustering. But again, I'm using those to also introduce this idea of supervised versus non-supervised. So, suppose we are now an insurance company. We've got out of the advertising game. It was good for a while, but we're bored with it now, and we've decided to go into insurance. So we have some historic insurance claim data. And by that, I mean we've dealt with the claims, and we have proved to our own satisfaction, and possibly in the courts, that some of these claims were honest and some were fraudulent. So for each case where somebody made an insurance claim, there's case one. These guys, we have some data about when the incident happened, what was the time, what was the postcode, what was the value of the items, how many items. We have a load of extra columns here. And we examined that case in the past and we decided it was not fraudulent. Fine. Bear in mind that this is a decision we have come to, and human beings looked at that case and made that decision. And you'll see that most of these cases aren't fraudulent, but if we have, I don't know, 10,000 cases to examine, we have a number where we prove to the court's satisfaction that this was a fraudulent claim. So we have the background data and we have this column here. Now, by this column here, I mean that this is our target. And by that, I mean, let's imagine we're doing this machine learning in order to be able to predict in the future whether new claims are fraudulent or not. So we have this background of 10,000 claims, but we find it expensive to get human beings to look at them. And we want to build a machine learning system when a new case comes in, it's got a new date, it's got a new time, it's got a new postcode, new value. We want to be able to feed that into the machine learning algorithm and have it tell us whether that case is likely to be fraudulent or not fraudulent. As a side note, machine learning is not magical. It is not going to tell you it was fraud or it was not fraud. It will give you a probability that that is fraudulent. It doesn't prove these people are innocent, guilty, but it can be very useful as a time saver. So in this case, we're using classification as an algorithm, which I'll explain in a minute. We are trying to predict, whether these claims are fraudulent or not. And the fact that we have this column that we are trying to predict makes this supervised learning. That's the long and short of it. Supervised learning means you have a column, a specific column, that you're trying to predict the value in that. You're trying to find fraud, not fraud. Now, you don't have to have a target, such as fraud, for machine learning. You may simply be trying to learn if there are trends and patterns. So I might have exactly the same data. I'll go back a slide. You can see what we've lost is this fraud column. It's entirely reasonable for me to take this data without the fraud, not fraud, and say, I'm just going to use classification as an algorithm on this. I'm just going to look to see if we have commonalities. It might, for example, tell us that an awful lot of claims happen in Scotland in the evening, and an awful lot of claims happen in Berkshire between 10 and 11 in the morning. I might use classification just to find those patterns. That would be unsupervised learning. That would be just saying, here's a load of data, find me the interesting patterns in it. So supervised means you have a target column. Unsupervised means you don't have anything specific in mind. You're just trying to look for patterns. And bear in mind, this is distinct from the difference between data mining and machine learning. With data mining, I said that you don't try and look at future cases and predict from them. Now, I might look at this data here. This has no target column. It might tell me that a lot of incidents occur in Scotland in the morning with male clients. A lot of incidents happen in Berkshire in the afternoon with female clients. I might describe those two groupings as type A and type B, and I might later say, here is some new data, is it type A or type B? So it's not supervised because I have no direct target I'm aiming at, but it's not data mining because I am actually using it to predict things in the future. So at first sight, the difference between data mining and machine learning sounds similar. They are quite different. Always remember, if you have a target column you're aiming at, it's supervised. If you're just looking for general patterns, then it's unsupervised. Okay, so there's lots of words in machine learning, lots of kind of definitions you've got to know. So here I've got the input columns, as they're known, and this is the target. So this is clearly supervised learning. So the classification algorithm is attempting to find which data or combinations of data in the input columns can be used to predict the target column, assuming I'm doing supervised. So it will spend a lot of time, if I go back a slide, it'll spend a lot of time saying, did we get fraud? Did we get a lot of fraud in postcodes with DD1? No. Did we get a lot of frauds with postcodes? So we're talking about classification as an algorithm, and really I'm using it as an excuse to introduce this idea of supervised learning and non-supervised learning. Sorry, I've just got to change glasses. Ah, that's what the screen looks like. Right. So what classification is trying to do is, oh, Mark, should we say if it does it again, we ought to, what do we do if it does it again?
We reschedule for another day, I think.
Okay,
because
yeah.
It's now we're only going to go until quarter. Well, we'll extend a bit, but you know, people put set aside the hours. So
yeah, no, that's what I meant really. So if I disappear, you know, probably by the time we've rebooted, it'll be okay. So classification looks for patterns. So it will try and find. It will look at this column and this column and say, well, do you get a lot of fraud where you have a postcode in Dundee, and that's Dundee Post, with high value items? It will look for correlations across the columns. And I said there are lots of names around here. I mean, you get these wonderful lists of people will talk about, well, how many predictors have you got? How many attributes have you got? How many dimensions have you got? They're all the same thing, guys. These columns you're going to use to classify the data, have a wild variety of names. They're all the same thing. And the same you will find as well. They'll say, how many cases have you got? Meaning, how many insurance claims have you got? Or they'll say examples, instances, observations. And I tend to call this the target column. You'll hear it called the output column, the response column. When I first learned about this, which was a long time ago because I'm very old, I spent ages trying to work out why do people use all these names? And it was because they like doing it, I think. So classification, important part here is this idea of supervised, where you're aiming towards a particular thing you're trying to understand, and unsupervised, where you're just looking for patterns. Clustering is yet another machine learning algorithm, a very useful one, one I commonly use. It is looking for behavior between continuous variables. So discontinuous variables are things, well, if I go back a couple of slides, that, for example, is a discontinuous set of data. Something like value of item is continuous. You can have any value you like between 350 and 750. These are discrete areas. Another really good example of a discontinuous set of data would be male versus female. Classification works very well with both continuous and discontinuous data. Clustering tends to only use continuous data, so multi-valued data. Now here we are looking at, for example, we may be trying to find honest, dishonest insurance claims. In fact, I go on about honesty and dishonesty in insurance, tells you what quite a lot of the commercial work I've done in the past has been about. I mean, it would be great. Maybe these are all the honest people and these are all the dishonest people. Wouldn't we love it if clustering was always as precise as that? But the idea of clustering is that you can plot one continuous variable against another, and you may end up by being able to say, most of the honest cases are here, most of the dishonest cases are there. Now, again, just to go back to this idea of a data model, what would the data model of that data be? That might be 20 million data points. Well, the data model for that could be as simple as this. If you have a normal distribution of points across there, so there are very few honest points here, very few honest ones there, but lots in the middle. And you have the same, sorry, I'm just fiddling around trying to get this pointer to work. And you have the same normal distribution there, then actually that entire cluster could be described in terms of the mean along this value and the mean along that value and the standard deviation here and the standard deviation there. In other words, that could be described in 4 numbers. That whole cluster could be described in 4 numbers. The mean value here, the mean value here, and the standard deviation in both cases. Same could be true of that. So the data model for that could be as simple as 8 numbers. And yet, if you have that data model and you feed in a new case and it ends up there, then the probability is very likely that that case is honest. If you get a point there, it's very likely that that case is dishonest. If it's smack in the middle, it's going to be 50-50 between the two. So you can take a huge amount of data, you can generate an incredibly simple data model, and you can use that model to make predictions about future events or about future, say, insurance claims. I'm really trying to show you the power of machine learning here. Why is it so powerful? So, I've shown 2 dimensions in that example. We could plot that in 20 dimensions. Nobody that I know can visualize data in 20 dimensions in their head. But the maths of that is not actually much harder than the maths for 2 dimensions. So we're almost finished. We have done, well, really everything in this list. We've even done thunderstorms. And they weren't even on the list, and we did those. We did lightning strikes. We've done everything this evening. One thing I haven't talked about are these 2, and I've left them to the end because these to me are very important, and they sum up a great deal about why machine learning is so important. So I've said I'll talk about deduction and induction, and I've said I will try and tell you why I think machine learning is so powerful. So those 2 go together. Now, Sherlock Holmes is famous for logical reasoning. I thought we'd give Dr. Watson the limelight for once. In a story called A Study in Scarlet, he's given some pills. He looks at them and he says, "From their lightness and transparency, I should imagine they are soluble in water." Now, what he's using there is what is called deductive reasoning. What do I mean by that? He has in his head, he probably learned it at medical school, something like that. I do know he's not a real person, incidentally. I'm not that much of a Sherlock fan. Pretty much a strong Sherlock fan, though. He's been taught a general rule about pills, which is that many pills which are light and transparent dissolve well in water. He's making a deduction about these specific pills from that general rule he has in his head. So if I tell you that all biplanes, or almost all biplanes, are very slow. And you see a biplane and somebody says to you, is that fast or slow? You'll think of the general rule and you say that's going to be slow. Now, deduction is taking a pre-built rule in your head and applying it to a specific case. Well, induction is the process of generating that rule. Somebody sat with lots of pills, popped them into water, saw which ones dissolved, and said, you know, if they're translucent and they're light, they generally dissolve well. If they're heavy and opaque, they don't. Somebody made a lot of different observations and created that rule, and that is called induction. Induction is creating the rule. Deduction is using it. Now think about traditional programming, and I'm sure the majority of you have done some programming. Programming is very often about encapsulating rules. If it's a biplane, then it's going to be slow. Otherwise, we don't know. If then else is what we use to encapsulate a rule. Okay, where did the rule come from? Well, it came from our heads. It came from the programmer's head, or it was given to the programmer by the financial director. But a human being performs the induction, thinks about the rule, creates the rule, and the programmer types it in. So you roll back to the 1970s, 80s, 90s, you think about Java programming, you think about C# programming. What you're doing is the human beings are thinking of the rules, the programmer is typing them into the program, and the program is running the rule. The program is doing the deduction, the human beings did the induction. That's a really important point, because what's happening in machine learning is the machine is doing the induction. The machine is working out what the rules are. We give it the data, it looks at the data, and it creates the rules, and then it applies them. But the crucial point is the human being is not creating the rules anymore. That is a much more serious, that has much more serious implications, for good and bad, than it at first sounds. But I'll stress it again, the huge power of machine learning lies in the fact that it takes over the induction of the rules. And the reason we want it to do that is that inducing rules can be very, very hard. Let me show you a picture. Here is a picture. Have a good look at it. Take your time. I'm going to ask you a question. I want you to get ready for this question. I want you to answer it as quickly as you can. Here we go. 3, 2, 1. And you were expecting a hard question, weren't you? It's obvious it's a car. I'm not giving anything away by saying yes, it's a car. Another question coming. Are you ready? 3, 2, 1. Well, it's not a taxi, is it? I mean, look at it. You're not going to commute in that. It's not an SUV. It's obviously a racing car. It's got big numbers on it. You found that, I hope, very easy to do. What I want you to do is write the rules you used down to make those decisions on a computer program. I want you to write a computer program that will make that decision as well as you did. I can't possibly do this. I can't write the rules. I don't know what rules I used. If we can get machines to start inducing rules, and we can get machines start inducing rules like this, it's machine learning that lets us do that. And once we can do that, we can get computers to do things that we as humans simply can't derive the rules for. So this is not a trivial change. This is a huge sea change in programming, in our relationship with computers, in everything. Just to make the point, think about autonomous cars, what is called so-called self-drive cars. They are not programmed by, if lady with pram crossing road and cat crossing road and brakes are failed, then run over cat. They are not programmed like that. They are using machine learning to learn what humans are doing in particular circumstances. Autonomous cars are just not even possible by normal programming. We can only do this with machine learning. There is no other way of doing it. So there's a lot of things like, I can hear thunder rumbling away again. So autonomous cars and many other technologies simply don't happen without machine learning. It's not kind of making stuff slightly better. It's making stuff possible that is totally impossible in any other way. And just because I've used simple examples all the way through this, I don't want you to think there is some like hidden complexity I'm not showing you. If you take neural nets, which are enormous fun, if you take that URL, if you drag a picture onto that, it will tell you what that picture shows. So this afternoon, I dragged that picture onto that URL, and it came back and told me this. And it's telling me that it's 100% certain that's a land vehicle. It's 99% certain it's a vehicle. The only thing it really gets wrong in that is it thinks there's about a 50-50 chance it may be a Mercedes-Benz SSK. The last Mercedes-Benz SSK that I know that sold was in 2013. It sold for 7 million euro. So I really, really, really wish that was true, but it's not. Now, that is using exactly the same process that I've shown you. So, who is it? Microsoft? Oh, it's Google, sorry, some big corporation. They have taken millions of photographs of the internet, and they've got people to classify those photographs, or they've taken the text that's around them. So what they feed in to what the data they start with, sorry, I'm just trying to get, here we are. They have the picture, and they have a description of that a human being has created. They've got the picture and they've got a human-generated description. That's their data. They've chosen an algorithm, and it's a neural net. These are very pretty things when you draw them. They created the model by feeding in the picture and the description in each case, and they feed in millions of these. That creates a model, and there is the model, and red and blue represent colors here, so the model's changed as the data has been fed through. Then we take the picture, we feed it into the neural net, and it spits out a description. It is exactly the same process I've shown you. That's what machine learning is. And if you can understand, or if you understand that, you genuinely understand machine learning. There's a lot of detail you may need to add to that, but that's the fundamental principle right there. That's it. Thank you very much.